formulate the system itself and outline it all the most important parameters in this system. So now let's proceed to the local asymptotic solution. As I already mentioned to you that we have local asymptotic solution, first of all, which was found by Roberts and Busse. It has very local nature, but has very famous history. And then in this history, this local asymptotic solution was raised from the proposal that the Ekman number is very small, and consequently we consider the differential layer or cartridge bell structures. So I just remove this stuff. Okay. Okay, now we proceed to the chapter 5.2. Not chapter, more precisely to say maybe paragraph. It's local asymptotic. As already mentioned, it's first of all it's related while the Roberts was first, but nevertheless Busse made more in this respect, and Roberts. And of course it was other researchers not so well known. So the first solution for the problem of convection in a rotating spherical shell in the limit of small Ekman number and with internal heating was found by Roberts in 1968 using WV-KB approximation. Busse use WV-KB approximation. And Busse in 2 years studied the onset of convective instabilities of a cell gravitation internal heated rotating fluid sphere. The results of the perturbation theory for this problem showed to be in agreement well with the results of the extension of the analysis by Roberts. Before that, 2 years before Busse, it was analysis by Roberts, but Busse actually introduced all this equation, which we already discussed it with you, but and nevertheless he used it like that. So then the constraining effect of the change in depth in the direction of the axis of rotation, as well as the gravity force and the basic temperature gradient, depend on the distance from the axis. Actually, this is actually dependent on the cylindrical distance, and of course to work well in this semi-geostrophic approximation. And his work, Busse, found the onset of the convection and was obtained by the Busse in the form of so-called very well-known cartridge bell of rolls, like that. And it was also experimental confirmation of that. A schematic view of marginal convection inferred from this asymptotic analysis is actually given in this figure of Busse. Convection is expressed to take the form of an ensemble of Taylor column aligning along a cylindrical spherical coaxial to the axis of rotation, like this. Oh, there is no picture. This picture, sorry, I found it later, but nevertheless, this picture actually. First I show you experimental picture of this stuff, but also there is the picture which is going from the asymptotic, and you see that there is original sketch of cartridge belt geometry of the magnetic instability convection motion in the internal heated rotating sphere. And this is sort of the cartridge belt of the structure. This is famous Taylor columns. While the Busse invented these columns and drawn this qualitative picture. And you see that these columns are very, very thin in this direction, which is azimuthal direction in the, on the cylindrical coordinate from the axis of rotation. And it's very prolongated in this way, so there is almost no dependence on that coordinate. And this is exactly goes in the way that we already studied with you, talking about the geostrophic flow. Let's now return to our estimation. And also was experiment, but maybe we'll discuss it later. So the basis of Robert Busse local theory is the assumption that the onset of convection is in the neighboring of critical cylinder. So there is some critical cylinder. Critical cylinder S equal S C critical S critical. Equation 5.4, which we got before that. Okay, actually the same equation can be linearized near the onset given. So actually we linearize the equation, and this linearization results in this following system. We already show you our equation, but here to consider the onset of the convection, we should linearize this system, and this is quite simple trick to linearize this system. You can do it by yourself, but nevertheless the final result I will write down under some simplifications. So it looks like that. Of course, the divergence is free, first of all. Then we have Navier-Stokes equation. It's important to mention that if we linearize the system, we give rid of V grad V term. Here we have only partial derivatives in time from substantial derivatives. So this is maybe greatest simplification. And here we have plus Coriolis force in non-dimensional form. Then we have gradient P. And of course we have this stuff which is related to the buoyancy term, Ekman number, Rayleigh number, this tau which work on the convection, and spherical radius. And final is effect of the viscosity. Okay, this is 5, 6a b. And then we have equation, heat equation or temperature equation, which include Prandtl number d tau by dt. Again, we give rid from the nonlinear term of the substantial derivative. This is the second place where we use this advantage. And so it's actually equal H. Busse used not Ts like we use, but he used this H straightly for the gradient of the corresponding velocity. No, not velocity. The gradient of the corresponding temperature which derives the convection. So he straightly used the value which is, like h, and it depends only on spherical radius. And here we have multiplication of the vector v by the vector r, scalar multiplication. And it's obviously that this is r component of v times the spherical radius r. And then, of course, there is the diffusion term, which could be written like that. And this constitutes equation 5,6c. Okay, so actually we can specify here, directly here, that if we have internal heating, then this h is just 1. It's internal heating. And in the case when this h is equal (1 over r cube), this is case of the differential heating. So just see that if you here we have additional r. So in fact, when we apply this stuff here, we have 1 over r. We just have r, and when we apply this here, it's 1 over r squared, effectively because we have on top here r. So to begin the small Ekman number asymptotic analysis, we said it's important to use exactly to solve the divergent Fay condition, and this is the simplest way is to use the stream function. And this stream function in this geometry which we used here is actually based on the cylindrical coordinates. And more precisely, even not cylindrical coordinate, but on the axis of rotation, because axis of rotation and rotational effects are dominated here, and actually they contrast everything. So to begin with the small Ekman number asymptotic analysis, we said the following, that V is just equal rotor C and unit vector in z direction. And we define one component, if you like, toroidal component of the velocity in this way. And a similar way we define the poloidal component, which contains double rotor. There is rotor of the next rotor of Xi to make it more pretty. Let's allow like that. Rotor. Oh, sorry. Again in that direction, and we multiply by that. Oh, maybe better to put that way. We are taking the rotor. Okay. I was done mistake. I put extra here. More convenient to write like that. This is the rotor, from rotor, and here there is C function, and in direction, unit direction of Z, and here there is, we close the brackets. So this constitutes formula Pi7. In this standard toroidal-poloidal representation, it's actually toroidal part and poloidal part. You see that everywhere we have rotor. So this selection of the velocity field automatically satisfies to the divergency condition. So we could give rid at least with one equation. So the one equation becomes less. And also we have another advantage of this approach, that instead of the 3 components of the velocity, we have just 2 components for the stream function. Here exactly for the stream function, and this is some analog which go in the poloidal component. So this is toroidal component, and this is poloidal. And it's quite standard notation. And this standard toroidal-poloidal representation, the velocity field satisfies the solenoidal condition, as I already told, and the corresponding vertical velocity and horizontal Laplacian operator are defined as. It's important to stress that this, in the case if we consider first of all the Coriolis part, if we consider the Coriolis part of the velocity, which is of course rather important. And it's just very simply could be obtained here via the, sorry. Okay, so we just notice it like we define this value, which is the scalar product of the velocity and the unit vector in direction of the Z. We define this value because it's quite important value. Actually, it's the component which is constitutes the velocity component in the direction of rotation. And later you see that it's indeed very important stuff. And in terms of all these things, it also has very simple representation via the modified Nabla square over Xc, and his constitute formula 5,8. And also we can define this operator, this modified operator, which is actually working in cylindrical coordinate. Please does not mistake this cylindrical radius with the entropy. Now we are not speaking about entropy, so but this is cylindrical radius. And this operator, delta square h, is 1 over s d by ds. And here s d by ds. And then there is azimuthal contribution 1 c, oh sorry, s 1 over s square d double on d phi squared, and this 5/9. Okay, you see that there is actually the fraction of the major fraction, maybe 2/3 the ordinary Laplacian, of course, square is here, of the ordinary Laplacian, but there is no z contribution here. So this is the difference. So it's make like the h, so mean horizontal. So it's sort of the horizontal in horizontal plane, not in the direction of rotation. So following Jones et al., Jones actually Sword and Musa, we insert 5, 7. Okay. Okay, we already passed that. So now we proceed further. And following Jones and Sword and Musa, we insert 5, 7 into the radial component of the cool and double cool of the momentum equation 5, 6b to obtain. So we use 5, 6b and insert all this representation to this equation. So eventually we obtain rather complicated system which is working like that. Okay, I have to remove. Okay, I don't know, is it enough space here? No. I don't know. Oh, maybe I'll better remove. Okay, just to simplify the things, let me not to rewrite all this equation. Moreover, it's already completely written here on the screen. I will just comment on the screen. I will not write down again this equation. It's quite lengthy. So perhaps I'll better comment on the screen. Okay, the first equation. Okay, I will comment with the mouse. Maybe it's easier. Okay. Here you see on the screen the first equation which we obtained by substituting the previous representation via the stream function and all corresponding function. Of course, we put it in the Navier-Stokes equation. And first of all, we see z component of this equation. It's the most simple one because there is no Coriolis force here. There is only contribution from the divergence on the time partial derivatives. Also, there is some things which is going after the value after viscosity. Oh, okay, I was wrong. There is Coriolis. No, it's not Coriolis contribution. Actually, it's coming from the pressure. And also there is some stuff which is also related the buoyancy contribution. It's here. And there is another component. Actually, there are only two components. And there is another component of this Navier-Stokes equation, which is written down here. It's a bit more complicated, but nevertheless, it includes everything, including Coriolis contribution here and everything. And also there is the form of the temperature equation, which takes the form. And here there is the main driving term, which is here. It's appear here. And also there is a form of this complete. So I will not repeat it on the blackboard. I think that you can write down if you like directly from this notation. Okay. So the Robert Busse localized asymptotic theory consider elongated structures of small horizontal scale such that, so they consider the following. This is now important thing. Okay. So first of all, they consider to have the all the structure in balance. They consider the derivatives of the in the azimuthal direction. They consider derivatives in the azimuthal direction, and they suppose that they are of order derivatives in the cylindrical direction, in direction of the cylinder. And to balance all this term in this equation, you can just check it, but it was checked by many persons, and you also could proceed with this checking. And then important balance is that all this d phi part, ds part, they are all acting like e to the minus 1/3. So each variable, each coordinate, we take the small variation of the coordinate here. So in fact, it's proportional e to the 1/3. And in the cylindrical radius, again, the same proportionality is working. So in some sense, it reminds you the Stewardson layer, maybe. And so it's actually quite natural. But there is some difference because here this layer is driven by the Busse force, but the very nature is about the same. So then other scaling is that d by dz, as we already saw with you on these interesting pictures from the experiment. You see that there is almost no dependence in z direction, and in this sketch you see also again that there is almost no dependence in z direction. So they are elongated like that, but here in this direction there is some concentration. So this is actually quite natural that the scale here is e to the 1/3. Okay, we considered that. So this value is of order 1. So this is the general view, and the solution then searched in the form. So we search for the solution. Actually, we can restrict ourselves by the z component of the velocity in this solution. Then we have function psi. Another contribution of the stream function which we considered before. This is actually contribution from the first toroidal term. And then we can write down the general solution. Of course, it also includes tau, temperature variation, and we just represent it. Maybe better to write down that it's not equal, but just proportional, because it could be some proportionality coefficient, which generally speaking depends on some. So it's proportional to the exponent of I, and then there is constant K capital, which multiplied it by S. Then there is M, which is multiplied it by phi. And finally, there is omega. Please not mistake this omega with rotational rate. And so omega t. Okay. I don't know, man. Not to mistake this omega with the omega we have previously and the definition of Ekman number. Let's make it small omega. In original paper it was like that, but nevertheless it's better to represent as small omega. And in the result, what we have, in result with this, this is quite simple representation. So you just take the exponent, so you represent as harmonic function in cylindrical coordinate, in coordinate of azimuthal direction, and in t direction we just have some engine value. No, with multiplied by I actually. This is the engine value because it's working like that. And so it's quite simple representation. Almost everybody knows such a representation via the expansion in cosine, sine, and exponent with this corresponding function. So it's quite well known things. And again, I will not write down the equation. This resulting equation are on this slide, which we obtain substituting this in the previous equation, which is look like that, this previous equation. So we substitute this representation to this equation, and eventually the great advantage that we eventually have this system of the equation. Of course, I will not repeat it on Blackboard, it will be too lengthy. So we have this equation, this set of the equation, and the major things for all this set is that we effectively remove cylindrical radius, azimuthal component, and time as well. We remove all this stuff from the system, and we keep only dependence on that. Oh, Rani is calling. Hello? No, we have this system, and here in this system it's important to stretch out the relation between all these values which are listed on this page, and also there is the surface of the sphere which are on this place. There is also the A coefficient which is actually represented like, I don't know. Okay, it's which actually this A coefficient is represented via the K, with this K. Then it's involved this M divided by S square, this S coming from here. But nevertheless, the most important message from this equation, first of all, of course, it's much more simple than initial one. This is, if with our initial equation was equation of the second order for 3 variables, so now we effectively have the equation, each equation is of the first order, and for just one variable, just one coordinate. So actually we simplify this system a lot. And so the next step is to estimate all this term of in this equation in order of magnitude. And Busse and Roberts did it in the following way. First of all, they estimated the real number, because it's the most important number. And it's scaled like e to the minus 4/3. Maybe I will use the mouse. because there is a tendency when I have a screen, I want to put it on screen. Okay, so we have this value, and here, okay, maybe I was wrong, that's use small omega. Okay, just put it like that. But you should distinguish this capital omega from the first omega which we used before that, because actually I don't know, it's such a big mess with the notation, but you should be careful that this capital omega is not the omega which we used on the beginning. So then we have this scaling for all this value. First of all, there is a Rayleigh number which scale like e to the 4/3 of the f, which is the scaled Rayleigh number. Then we can represent this omega which is responsible for the time period like e to the minus 2/3. And then we can represent this value k which is responsible for the cylindrical radius. It represents like this. And finally we represent all the functions, so in the relative extent that scale like this on the bottom. And then finally we can rearrange this initial system which I'll just already show to more simplified one, and it's written here. And actually it's almost the same system but with some reduction. So then we proceed further, and eventually all these three functions can be collapsed to just one, which is written here. And this is actually the things which is constitute the deviation, constitute the simplification from the previous system. We just neglect by one contribution, especially in this on the last row you see that there is no any derivatives, so it's the sort of the algebraic relations. And here you see also there is only one derivative and only one here. So effectively this is actually algebraic relation, and this one and this is the first order equation. So eventually all this system becomes just the equation, ordinary differential equation of the second order, which is written here as 5.15. And we can even reduce this system further, and we reduce it even at the boundary condition, of course. Here there is the system itself, but below there is the boundary condition at one boundary and at another boundary, one boundary at z equal naught, and another boundary at z equal this value of the cylindrical radius, which will be on the top, then we have taken the plus, or on the bottom, then we taken the minus, and in this case we apply this boundary condition. Okay. Okay. So actually this simple formulation replaces all the we have from the very start, but there are very many parameters. Let's now consider all these parameters in this system. And of course it's necessary to solve this boundary value problem for all these parameters, just taking on the value of all these parameters and estimated corresponding solution. So to construct the dispersion relation for our problem, we solve this two-point boundary value problem, this two-point boundary value problem, which is formulated here. 5.15, 5.16 for the complex eigenvalue omega. Here this complex eigenvalue omega appear here, and even, no, it's not appear in the boundary condition, but it's appear here in the equation. And following the scaling, m is no longer restricted to be an integer, and it is straightforward to find omega for any value of the parameters using standard numerical techniques. The objective of the local theory employed by Roberts and Busse is to maximize the growth rate. Actually, this is quite obvious objective. The growth rate, which is in terms of this omega, is imagined part of omega, and it could be maximized over all admissibly real s and k. S means the cylindrical radius, k means S means the cylindrical radius, this here, and k means the wave number in the phi direction. The imaginary models are then identified by the maximum value of Rayleigh number, which gives steady state solution. So this is the critical Rayleigh number which we necessary to find. Evidently, this local disturbance is neutral, neither growing nor decay in the space. And actually, imaginary part of k is a parameter which appears here, this k parameter, and it's is equal 0, and that's the later condition. So actually we define the, as we already told, we define this modified omega which comes from the, like the function of the following parameter. S cylindrical radius is plain like a parameter, then k, this is wave number which is played in phi direction, m, and also we are using modified Rayleigh number. In all this parameter space, we are looking for the most highest growth rate and correspondingly for critical values. And the object of the local theory employed by Roberts and Busse is to maximize the growth rate over the all possible real values. The marginal modes are then identified by the minimum value of the Rayleigh number R, which gives steady state solution. Evidently, this local disturbances is neutral, neither growing nor decaying in the space, and corresponding imaginary part is 0. Thus, the later condition, this is, perhaps it appears somewhere here as well. Okay, we have this. So everything we have on the picture, so we apply this condition and expand the imaginary part of omega in this way. And so this can be thought of as the equation determining the Rayleigh number R and with frequency real part of omega in the terms of S, K, and M, like it's written here. So we use this equation just equating to the maximum and then extracting from it the most suitable part of this modified Rayleigh number. So let us minimize R over n and fixed S and K. Then for n increment delta m, this increment delta m, which is shown here, we can expand it in this way. And since the minimum of the characteristic is characterized by the condition that z is equal naught, this is modified Rayleigh number. Its derivative is equal naught, so it constitutes the condition of critical condition. So, and then we have in 519, okay, it's written here also, everything is written here, so there is no need to repeat. So we identify all these minimal, maximal stuff in the imaginary part. And since the minimum O is characterized by this 0, then all this implies that the imaginary part of omega is also equal 0 in the different parameter system. And we stress that up to this point in the argument, the local theory and global theory, which we discussed below, are in total agreement. So there is a point where it's still in total agreement, but consider now minimization of over k and s by arguments similar to those used for 5.19, but involving increment decay and ds. Instead, we obtain the condition. So this is the point where there is a difference. This point states that we are developing the last two cases, and this is indeed the condition for the local theory. And this completes the determination of minimum RL or R over all real value of M and K and S. And the solution of the system of equation 518, this system of equation, and the following equation, so solving all this equation provides the local stability criterion values for which are identified by the subscript L. The result for critical parameter of the local theory are listed in table 1 of Jones for the set of different Prandtl number. So this is the numerical result. You see that for different Prandtl number we can estimate the result from the local theory. And here in brackets you see the result from the direct numerical simulation. You see that there is rather big difference. For example, here from the local theory we obtain modified Rayleigh number like this value, but in direct numerical substitution we obtain sufficiently smaller value. And there is also some difference here. There is also some difference here, but frankly speaking, not so much. But if we write the Prandtl number, so in this case, you see that the difference becomes more valuable. Maybe not so much different. And so actually this local asymptotic is, while could be re-estimated by the, could be accurate enough for our purposes, but still it's not so accurate as it requires from the general and so exact theory. So perhaps we finished with this paper which named the local asymptotics, and then on the next meeting of us we proceed to the global asymptotic. And now perhaps if you have some question, please raise them. The last line is that we are looking on the imaginary part of the derivatives of the omega, which is actually eigenvalue, in cylindrical direction, and on the condition that we keep this n constant. And under this condition, to reach the extremal point for the critical convection, we should satisfy 0. So this is the sort of the minimal maximal consideration which we are looking for just to identify the critical point.
Okay, sir. Thank you.
Okay, is there any more questions? Okay, I just draw the conclusion that this local theory, of course, not so correct, but it's still rather accurate. But nevertheless, to get the sort of the precise theory, we need to proceed further and to consider the global asymptotic, because this one is just local, and it just gives the extremum we are looking for at some local position in complex domain. But eventually it was the big breakthrough that when we considered some global position in this complex domain, and it was done by the Jones, Sowert, and Ali Musa. Okay, so maybe. But the major advantage of all this stuff, as far as I could see, that we reduce very complicated system. You saw it. It was the system of actually 8 order in partial derivative in all three variables. But eventually we reduce it just to the one coordinate dependence. And there is no actually no dependence of time because it's actually in engine value. And then we have a simple picture how this things is operated, and actually almost for any case we can have almost exact solution. But to get sort of the exact solution, we should make the next step, which I report you tomorrow on about the global solution. So, in some sense, we finished. Is there any more questions?
Sir, previous slide. Previous.
Yeah, one more question.
Previous. The scaling E equal to that Ekman scaling.
The scaling.
Scaling.
Okay.
Sir, here. Sir, how we can choose this type of scaling that R equal to R to E to the power?
Actually, we put this scaling when this is the initial system from which we extract this scaling. We just keep this term in each equation. We compare one term and another term. One and another. Sometimes we compare 3 terms. And to have the equation valuable, that it's not cancelled out.
Okay.
We suppose that there is balance between these terms.
Okay.
And first we suppose that these terms are in some arbitrary power. And then we just feed this power in the way that all these terms are balanced.
Okay.
So this is quite ordinary trick which we
Yes.
teach with you.
Hey, you did
When
before.
estimated Sturgeon layer, and so it's quite thing which is close to the estimation of the Sturgeon layer we consider, and it's exactly e to the 1/3, like a Sturgeon layer.
Yes. Yes.
So this is a quite ordinary trick, but not everybody plays that.
Okay. Thank you, sir.
Okay. One more question. Okay, perhaps we finish. Thank you for your attention.